All right, good afternoon, good evening, ladies and gentlemen. Welcome to another series of tutorials with me, Aubrey. In this lesson, we'll be looking at this integral. As you can see, we are integrating from negative infinity to positive infinity of x squared all over x plus x squared all raised to power 4 with respect to x. So basically here, what we'll be doing is whenever you are dealing with let me see, is it okay, when the integral that you're dealing with has a point where it is undefined, you can use Cauchy's integration to maneuver that integral. So since as you can see we have nth power there, we have the point where the function is undefined is raised to the power n. Okay, it means that we're going to use the Cauchy's formula for nth derivatives, okay, which is that there. So where you have n plus 1, this is equals to, you have f of z there. Now you should have z to the power 1 minus z naught, where z naught is the point where the function is undefined, which is equals to 2 pi I over n factorial multiplied by fn of z naught. This is the number of times you are going to differentiate your f of z. So if there's n is 7, you're going to differentiate f of z 7 times and later replace the point where the function is undefined. All right, so that is what you do. So now from here, we need to find the region in which we are integrating on. Right, so since we're moving from negative infinity to positive infinity, this means that we're dealing with the upper half of the entire complex plane. Okay, we're dealing with the upper half of the entire complex plane. So meaning that we are integrating in the entire complex plane, but we're dealing with the upper half of the complex plane. All right, so yeah, so this is our region of integration. Now we can kick start with the integration. Okay, and just a side note, the region of integration is very important because it tells us on which pause or which points of where the function is undefined do we need to focus on. All right, so if the pause that we're dealing with or the points that where the function is undefined are in the region of integration, or if they're outside the region of integration, we consider their integrals to be zero because it's outside the region of integration. All right, so let's dive in. So we're integrating from positive infinity to negative, from negative infinity to positive infinity. So first of all, we need to deal with this part here. So you can equate this part to zero and you write this as, you need to make sure that the power there is one. You need to write this as a product, okay, as a product that can give you the same number if you multiply. So simply you can just equate this to zero and solve for x, and what you get there will be the products. So as I did here, I solved for x and I got 2 points, which is x is equals to I and x is equals to negative I. Then I took them the other side of the equal sign, which is x plus I and x minus I. And this, when you multiply, will give you this. So we have achieved x should have 1 to power and this 1 to power. Then we have this 4 which should come here. So we have that 4. Then from here we know that we can distribute this 4 here and here. So this will give us that, like that. All right. So now after doing this, after doing that, we will have to separate uh, these two parts so that we achieve this formula that is right here. We need to make sure that our integral look like this formula here on this side of the formula so that we can apply this part of the formula right here. All right, so at the bottom there, we should only have one part that is giving us a pole. Okay, one part is that is giving us a pole. But since here there are two parts that are giving us a pole, as you can see, there are two parts, so they will take turns to be the denominator. So this is what we mean. So this one will take turn to be the denominator, okay, like this, then plus the other part will also take turn to be the denominator like that. So you have two answers. So if there were three parts, we have one part raised to power 4, the other part raised to power 4, and there was another part raised to power 4. We would have three uh, parts taking turn to be the denominator. All right. So now this now, as you can see, looks more like the integral right here. Okay, looks more like the integral right here. So whatever we have on top there, that is our f of z, and what we have there is the point that is giving us the pole. So what we have there is our f of z and the point that is giving us the pole. So here we check for the poles. So the pole here, we equate this to 0. So equating that to 0, that is our pole at this point. And equating this to 0, that is our pole at this point. Now, what is important here is why is it important to find the poles? Because, well, the poles tell us which integrals to focus on. Okay, so if the pole is outside the region of integration, we consider the integral on that pole to be 0. So if this is outside the region of integration, this entire thing is 0. And if this is outside the region of integration, this entire thing is 0. And we can end here, and our final answer would be 0. So we need to counter check. So there our pole is x equals to negative I, and here our pole is x equals to I. So which among these is inside and which one is outside? So the region, we see that here we have positive i's and here we have negative i's. All the negative i's are outside the region of the integration, meaning that this pole will be outside the region of integration. Hence, the integral of this part will be 0. Hence, we will only have to deal with this part. All right, so now we say this is equal to, so the first part integral is 0. Then we now need to only work with this part. So this is our f of z, okay? And this is the part that is giving us the pole, which is just similar to this formula right here. I don't know where the formula is, the formula right there. So we are following this formula right here, as you can see. Okay, so now say f of z is that, and x naught is our pole, which is I. So now the integral, we now replace in this formula. Okay, we're replacing in this formula. What is our n? What is our n? So we say here there should be n plus 1. So when you look at here, n plus 1 would be 3 plus 1, meaning that our n is 3. Okay, so meaning that here we can put 3, okay, and here we can put 3, okay, and so yeah, so that is equal to that and that. So now what this is telling us is that we need to differentiate f of z, which is this, 3 times, and what you're going to use to differentiate this 3 times is the quotient rule, because you have a quotient like that. So you differentiate this 3 times, and after you differentiate 3 times, the third derivative you replace in x naught like that, then you multiply to that, and that will be your answer. So I will do so the first, I've already done the 3 times integration or differentiation. I've already differentiated 3 times. So the final answer will be this, that. So this is the third derivative. So uh, send me your second and first derivative. I check with you. I'll put the email in the description and you can get in touch. So, but this is the third derivative. Then, yeah, so from here, we just now need to find f of x naught, and our x naught is I. So we replace I everywhere here. So after doing that, we're going to get that, okay? And here we can separate We can separate. This is 7, 2 to the power 7, and I to the power 7. Okay, and the top part, when simplified, that would be negative 48. And down there will be 2 to the power 7 and I to the power 7. Now, what is I to the power 7? Okay, I to the power 7, that is, can be split into two parts. That is I to the power 3 times I to the power 4. Now, since the bases are similar, it means that the powers can add up and you get I to the power 7. Now, I to the power 4 is the same thing as uh, negative 1 times negative 1, which is just 1, then I to the power 3, that is equal to negative I. So down here, we can replace negative I and 2 to the power 7, which is 128. When simplified, that is what you're going to get right there. That is what you're going to get right there when you simplify. And replacing in the formula, you get that. And our f of z, which is 3 over 8i. So now our final answer, this will be our final answer, but we can see that I there and the I can cancel out. 2 there, it's 1. 2 there can go there how many times? That is 4 times. Then 3 factorial, that is 3 times 2 times 1. So 3 and the 3 can go there. So from there, that is just 2. So the final answer will be pi. Use the white pen. So our final answer will be pi all over 2 times 4. That will be 8. So that will be our final answer. All right. So this and that would remain with 4. The I and the I will go. Then these 3 and the 3 from the 3 factorial will remain with 3. Then yeah, you say 2 times 4, that would be 8. And that is our final answer. So if you have any question, you can leave that in the comment box.